السلام عليكم. انا رجعت لكم تاني. انا معاكم دكتور احمد عيد، وان شاء الله دلوقتي هناخد اهم موضوع بالنسبه لكم، الكيميكال فورمولي، الايكويشنز والكالكيوليشنز. وطبعا انتوا اكيد عارفين ان الموضوع ده كومن موجود في يونت 1 ويونت 2. هو ده وجزء البريدك تيبل هو التو توبكس اللي موجودين في التو يونتس. احنا هنتكلم بالتفصيل على الكيميكال فورمولي، الايكويشنز والكالكيوليشنز. اتمنى تكونوا خلصتوا الفيديوهين الاولانيين اللي انا نزلتهم لكم من المراجعه. اتمنى تكون المراجعه دي قادره انها تساعدكم، وان شاء الله تعملوا حلو بكره في الامتحان. ما تنسونيش بدعوه حلوه وانتوا بتمتحنوا، ويلا بينا نبدا الليسون بتاعنا. We'll talk now about chemical formulae, equations and the calculations. It's divided into two parts. We'll take part 1 right now. At the beginning we want to know how to write equation. Two types of chemical equations. We can write two types of chemical equations. One of them is called word equation, and the other one is called simple equation. Simple equation usually called chemical equations, and you should only write a word equation if he asks you to do word equation. If not, all chemical equations must be balanced and written in simple form or simple equation. Let's check first one. An example of balanced chemical equation: CaCO3 calcium carbonate plus 2HCl gives CaCl2 plus carbon dioxide plus water. Another balanced chemical equation: if you check the first equation, 1 calcium on both sides, 1 carbon on both sides, 3 oxygen, 2 and 1 equals 3, 2 hydrogens, 2Cl, 2Cl. Another balanced chemical equation is H2S2O7 plus H2O gives 2H2SO4. If you have brackets in a formula like CaOH by 2, you have to know that 2 multiplied to hydrogen and 2 also multiplied to oxygen. 2 oxygens and 2 hydrogen atoms. The small number refers to everything inside the brackets. For example, CaOH by 2, the 2 is applied to both oxygen and hydrogen. The formula shows 1 calcium, 2 oxygen, and 2 hydrogens. When we talk about balancing chemical equation, in chemical reactions, you must always end up with the same number of atoms that you started with. Check this example: CH4 plus 2O2 gives CO2 plus 2H2. If we check this image, as you can see this image, methane CH4 reacted with 2 oxygen molecules to give 1 molecule of carbon dioxide and 2 molecules of water. 1 carbon right here and 1 carbon right here, 4 hydrogens and 2 hydrogens here and 2 hydrogens here, 4 hydrogens. 4 atoms of oxygen or 2 molecules of oxygen, 1, 2, 3, 4 atoms of oxygen. So take care that when you balance equation, number of atoms before and after the reaction must be the same. He asks to balance this equation, reaction between zinc and hydrochloric acid. As you can see, 1 zinc, HCl, 1 hydrogen and 2 hydrogen in the product. So you have to multiply by 2 right here. Just writing 2 right here. Now the equation is considered as balanced. Take care of this. Never change a formula. You cannot say HCl2, for example. You cannot change formula. When balancing an equation, all you are allowed to do is to write big numbers in front of the formula. In fact, it's acceptable to use half in equations, but you do not usually come across them in IGCSE. You may find it in AS level. If you argue that you cannot have half an oxygen molecule, for example, to remove the problem, that problem double everything. If you have fraction, you can double everything and remove this fraction. You need to know 4 different state symbols solid S, liquid L, G for gas, and AQ for aqueous solution. Aqueous solution means dissolved in water. So an equation might look like this: 2K solid plus 2H2O liquid, take care water is considered as liquid, not aqueous, gives 2KOH aqueous plus H2 gas. This shows that solid potassium reacts with liquid water to make a aqueous solution of potassium hydroxide in water and hydrogen gas. Remember that water is considered as a liquid, not an aqueous solution. Aqueous solution is formed when something is dissolved in water. Let's talk about relative atomic mass. He may ask you to define relative atomic mass. The mass of atom and the molecules are compared with the mass of an atom of carbon-12 isotope. We call it carbon-12 scale. It's like this image. Check this. We compare any atoms with carbon-12. Carbon-12 is considered as our reference. The most common hydrogen atoms weigh 1/12 of carbon-12 atom. On this scale, the relative atomic mass of chlorine is 35.45, lithium 6.94, sodium 22.99, and because we are considering different isotopes and quoting the average mass, but in IG, in international system, we only use relative atomic masses, for example, decimals or fractions. In chlorine, Cl 35.5 and the copper 63.5 only. Other elements considered as whole number. For lithium 7, not 6.94, for sodium 23, and as I told you before, periodic table will be provided with you in exam. When we talk about relative formula mass, if you are talking about compound, you can use relative formula mass. Relative formula mass is sometimes called the relative molecular mass, and the relative formula mass symbol is MR. Calculating some relative formula masses. Easiest part. Find the relative formula mass MR for magnesium carbonate, MgCO3. Magnesium 24 from periodic table, carbon 12, and oxygen 3 multiplied 16, so MR will be 84. Find the relative formula mass for calcium hydroxide. Remember this. We just mentioned that we have 2 oxygen and 2 hydrogens. So 16 plus 1 times 2 plus 40 for calcium, it will give 74. Find the MR of copper 2 sulfate pentahydrate. Pentahydrate contains 5 water molecules. So we can do it. Copper 63.5, sulfur 32, oxygen 4 multiplied 16, and for water 18, but multiplied 5. So 5 multiplied 18, it will give 249.5. And this, for clarification, you can see that copper sulfate attached to 5 molecules of water in the crystal solid. Let's start talking about the mole. In chemistry, the mole is a unit of the amount of substance. For example, if we talk about 1 mole of water, it has a mass of 18 grams. Water, we just mentioned, 2 for hydrogens, 1 and 1, and 16 for oxygen, adding them together give 18 grams. 1 mole of sulfur from periodic table has a mass of 32 grams. 1 mole of magnesium oxide, MgO, mass 40 grams. Mole can be written as MOL. For example, the amount of water as 36 grams, you will find it's equivalent to 2 moles, just dividing 36 grams over 18 mR. 1 mole of water has mass of 18 grams. 36 grams of sulfur 32, so 36 divided by 32, it gives 1.125 mole. 36 grams of magnesium, 1 mole is 24, so it gives 1.5 mole, because mass of 1 sulfur is 32 as I mentioned, and mass of 1 mole of magnesium is 24, and this obtained from the periodic table. Let's talk about some examples calculating the mass of a mole of substance. 1 mole of oxygen gas. Check this. 1 mole of oxygen gas, relative atomic mass of oxygen is 16. So mR of oxygen, 2 multiplied 16, because it's O2, it gives 32. So 1 mole of oxygen, O2, has mass of 32 gram. 1 mole of calcium chloride, CaCl2. Calcium is 40 and chloride is 35.5 for each one. So 40 plus 2 multiplied 35.5, it will give 111. So 1 mole of calcium chloride has a mass of 111 gram. 1 mole of iron 2 sulfate heptahydrate, 7 water. Iron, as it mentioned, 56, sulfur 32, oxygen 16, hydrogen 1. So we can write it as 56 for iron plus 32 for sulfur plus 4 multiplied 16 for oxygen plus 7 multiplied 18 for water. It will give you 278 gram. So 1 mole of iron sulfate, iron 2 sulfate, hydrated form iron 2 sulfate, gives what we calculate. Note that whenever you talk about mole of something, you must quote its formula. He mentioned O2, because if he didn't mention, we can think it's O1, or oxygen. Oxygen molecule is O2, but he may ask about oxygen atom, for example, 16. So you must quote the formula. We mentioned iron 2 sulfate crystals. We didn't mention water, but he writes the formula. For example, as I told you, 1 mole of oxygen atom, mass of 16, while 1 mole of oxygen molecules, O2, mass is 32. We often use the term molar mass instead of mass of 1 mole, and now we'll use the triangle interconversion between mole and mass. If you check this, you can interconvert between mass in gram and the amount in mole for a given substance using this triangle. If you're asking about mass, you can multiply number of moles times mass of 1 mole, mR. Mass in gram equal number of moles multiplied mass of 1 mole, which is called mR. If you want to calculate number of moles, just dividing mass in gram over mass of 1 mole, molar mass. If you want to calculate mass of 1 mole, mR, divide mass over number of moles. Let's take some examples. First one, find the mass of 0.2 mole of calcium carbonate. We are talking about calcium carbonate. As you can see, calcium carbonate, we have to calculate mR. 40 for calcium plus 12 for carbon plus 3 multiplied 16 for oxygen. It gives 100 mR. 1 mole has mass of 100, but he told us 0.2 mole. Mass is equal to number of moles multiplied mass of 1 mole. 0.2 multiplied 100 gives 20 gram. So 0.2 mole of calcium carbonate has a mass of 20 gram. The other one, find the number of moles in 54 gram of water. Actually, mR of water 18. We calculated several times. So number of moles is equal to 54 divided by 18. It gives 3 mole. So 54 gram of water contains 3 mole. When we talk about formulae, we have different types of formulae. Empirical formula, for example, is considered as the simplest whole number ratio of the atoms present in a compound. While when we talk about molecular formula indicating or shows the actual number of atoms of each element present in molecule. In case of covalent compound, or present in formula unit. In case of ionic compound, when we talk about ionic compound, we cannot say molecule. We just say formula unit for ionic compound, and the molecule can be used for covalent compounds. The molecular formula can be the same as empirical formula, or even a multiple of the empirical formula. The empirical formula of calcium oxide, CaO, and the molecular formula also CaO. The empirical formula of hydrogen peroxide, HO, while the molecular formula is H2O. O2. Let's talk about working out empirical formulae. First example, a sample of compound contain 1.27 gram of copper, 0.16 gram of oxygen. Calculate the empirical formula and AR of copper and oxygen given. The easiest way is to do this in column using a table. Just writing copper and oxygen, mass provided 1.27, 0.16 for oxygen. Find the number of moles of each one by dividing mass over mass of 1 mole or molar mass. So 1.27 divided by 63.5 and 0.16 divided by 16. Then after you calculate the number of moles of each, divide by the smallest one to get whole number. You will find that the ratio 2 to 1, this means Cu2O, empirical formula of this one. When we talk about example 4 sample of compound containing 0.78 gram of potassium, 1.10 gram of Mn, and 1.28 gram of oxygen, and AR provided. Just writing K, Mn, and O, mass of each one provided, divide by MR of each one, or AR, it's element, AR, dividing by AR of each one, and then divide by the smallest. The smallest one, 0.02, divided by 0.02, all of them, gives 1 to 1 to 4. So the empirical formula will be KMnO4. In this part, we will talk about several practical experiments investigating the formula of a metal oxide by combustion, just by burning. We use magnesium ribbon. We just heat it and use a crucible with lead. He may ask you, give one safety precaution, wear eye protection, take care not to get burned. When raising the crucible lead, use tongue. The crucible will stay very hot for some time. Let's see the procedure. We can find the formula of magnesium oxide by burning magnesium ribbon in oxygen and looking at how the mass changes. You know that the mass will increase because it converted from magnesium to magnesium oxide. The following procedure is used. Weigh a crucible with a lead. Place a piece of magnesium ribbon about 10 centimeters long in the crucible and weigh the crucible and contents. Set up the apparatus as shown in the figure above. Heat the crucible strongly using roaring flame. Roaring flame means blue flame. Lift the lead every few seconds. Why? To let oxygen get in. When the reaction is finished, allow the crucible and content to cool. Weigh the crucible and content. When you weigh it, wait it to cool. Don't weigh it while it's hot. When the magnesium burns, it does so with a bright white flame, and magnesium oxide forms, which is considered as white powder produced during this reaction. A lid is placed on the crucible to prevent the white powder, which is magnesium oxide, escaping. But the lid must be lifted every few seconds to allow oxygen into the crucible to react with magnesium. How do we know when the reaction has finished? We can generally see when there is no more reaction because nothing is happening in the crucible. We can also check by weighing the crucible and content, then heat and weighing again. Keep heating and weighing until constant mass. You may ask about this part tomorrow. A set of results for this practical could be empty crucible 32.46, mass of crucible plus magnesium 32.70, so by just subtracting this from this gives the mass of magnesium. Mass of crucible plus content at the end of experiment 32.86, just subtracting this one minus this one gives mass of oxygen. We can work out the mass of magnesium by subtracting the mass of crucible from the mass of crucible plus magnesium. It gives 0.24. The reason that the mass increases is because magnesium combines with oxygen in the air. The mass of magnesium oxide is greater than the mass of just magnesium due to the extra oxygen. We can work out also mass of oxygen combined with magnesium by just subtracting 32.86 minus 32.70. It gives 0.16. In order to find the formula of magnesium oxide, we need to work out how many moles of magnesium atoms combine with how many moles of oxygen atoms. Just use masses. We just calculate masses. Divide by mass of 1 mole. For each one, 24 for magnesium and 16 for oxygen. You will find that 0.01, both of them, divided by the smallest, gives the ratio 1 to 1. So it's MgO. When we do this experiment in practice, it's not very often that the ratio come out as 1 to 1. He may ask you about this part tomorrow. There are things that may go wrong with this experiment which could affect the results, such as some of the magnesium oxide powder might escape when the lead is lifted. We have to open the lead several times, it may escape. Not all the magnesium might have reacted. We have to check the mass and take care constant mass. The magnesium can also react with nitrogen in the air. Let's take another practical investigation, which is the formula of metal oxide, but this time by reduction. We can also find the formula of oxide by removing oxygen from it and looking at how the mass changes. The mass will decrease in this case. The following procedure can be used to find the formula of copper oxide. Weigh a ceramic dish like this, copper oxide in ceramic dish. Put about 3 grams of copper oxide in ceramic dish and weigh the dish again. Place the ceramic dish in tube like this, as shown in figure. Pass hydrogen, stream of hydrogen gas from here, and excess hydrogen must be burned in the other side. Ignite the excess hydrogen which comes out in the small hole of boiling tube. Heat the copper oxide strongly until the reaction is finished. You know the reaction is finished that pink-brown copper metal will be seen, not the black oxide. Some notes. We must always make sure that the tube is filled with hydrogen before lighting the stream of hydrogen, because a mixture of hydrogen and oxygen is explosive. If you just light or heat like this and oxygen and hydrogen right here, it may explode. So just move a stream of hydrogen until the hydrogen comes out from this side, then start to heat. It's important to let stream of hydrogen gas flow through the tube for a little while to flush out all the oxygen, get the oxygen out, before lighting it or lighting a Bunsen burner. This is displacement reaction or competition reaction. Hydrogen is considered as more reactive than copper, so it displaces copper from copper oxide. Displacement reaction will be discussed later. We have set of result, as we mentioned, empty dish plus copper oxide, mass of dish plus content at the end of experiment. You can see that mass decreases. The reason that the mass decreases because hydrogen combines with oxygen from copper oxide to form water, and the oxygen is removed from copper oxide and left only copper at the dish at the end of the experiment. Because oxygen is removed from copper oxide, we say that copper oxide reduced. Reduction will be explained also later. From this data, we can calculate mass of copper oxide at the beginning by just subtracting the mass of dish from the mass of dish plus copper oxide. Now we have the mass of copper oxide. We can also work out the mass of copper remaining at the end, just subtracting 26.32 minus this one. It gives the mass of dash plus copper, and subtracting both of them from each other gives the mass of oxygen removed. So we have 2.54 gram of copper with 0.64 gram of oxygen in copper oxide. We can deduce the formula. As you can see, mass of copper, mass of oxygen divided by AR, 63.5, 16 in this case, it gives 0.04, divided by the smallest, it gives 1 to 1. The equation for the reaction is CuO plus H2 gives Cu plus H2. This is considered as displacement reaction because hydrogen displaced copper, and also its redox reaction. Copper lost oxygen, so it's reduced, and hydrogen gained oxygen, so it's oxidized. We can also determine the formula of water by almost the same procedure, but with some modification. It's like water vapor condensed right here by a mixture of ice and cold water in this U-tube, and find the increase in mass of tube. The experiment is conducted in the same way, except water vapor produced in the reaction of copper oxide with hydrogen is condensed right here. The content of the dish at the beginning and at the end of the experiment weighed again. The mass of water corrected in U-tube must also measured. Mass of water is the increase of U-tube. Same data, but with mass of water mentioned. The mass of oxygen lost, we just mentioned 0.64. All oxygen lost from copper oxide combined with hydrogen to form water. This means water contains 0.64 gram of oxygen, 0.72 gram of water was corrected, so mass of hydrogen will be from subtraction. To determine the empirical formula of water, we have hydrogen and oxygen, divide by AR, then divide by the smallest, you will find it H2O. Working out formulae using percentage composition. In the worked example and the practical example above, we have determined the empirical formulae of compound using masses. Now we will use it as percentage by mass instead of masses. He may ask you a question like this one. You have 82.7% of carbon and 17.3% of hydrogen. You just suppose that the mass in 100 gram, then divide by AR for each one and divide by the smallest. But now we get 1 and 2.5 for hydrogen. 2.5 is not acceptable, so you have to multiply both of them by 2. So we have 2.5 more of hydrogen atom to every carbon atom. Empirical formula must be whole number ratio, so the whole number we have to multiply by 2. You will get C2H5, which is considered as the empirical formula. Now let's start converting empirical formulae into molecular formulae. The molecular formula is considered as the actual number of each atom present in a molecule has to be multiple of C2H5. Just multiply it by 2, by 3, and so on. So it's like C4H10, for example, if you multiply it by 2. We can find the molecular formula if we know the relative formula mass of compound, let's say mass of 1 mole, MR in grams. In the previous example, suppose that the relative formula mass is 58, and the relative formula mass of C2H5 is 29. Just divide 58 over 29, you will get 2. Then multiply 2 by C2H5, it will give C4H10, so the molecular formula is C4H10. Let's check this example. A compound has empirical formula CH2 and relative formula mass 56. Work out its molecular formula. Easy one. Carbon 12 plus 2 multiplied 1 equal 14, and 56 provided relative formula mass. 56 over 14 gives 4. So we have 4 of CH2. This means 4 multiplied CH2 equals C4H8. Remember that the ratio of elements in the molecular formula must be the same as in empirical formula. C4H8, if it cancels down, it gives CH2 again. When we talk about empirical formula calculations using or involving water of crystallization, when some substances crystallize from solution, water becomes chemically bound up with the salt. This is called water of crystallization. The salt is said to be hydrated, while anhydrous salt means without water. Let's say barium chloride crystals in crucible, just heat it and you will find that it contains water of crystallization, as you will see. Usually, when you heat a salt that contains water of crystallization, the water is driven off, leaving anhydrous salt behind. If you heated barium chloride crystals in crucible, you might obtain these results. Mass of crucible, empty crucible, 30 gram. Mass of crucible plus barium chloride crystals within water, you don't know exactly how many molecules of water in the formula. It gives 32.44. And mass of crucible with anhydrous barium chloride, 32.08. Just subtracting this one from this one will give mass of water. And subtracting this one minus empty crucible gives mass of anhydrous salt. So to find the N, find the ratio of the number of moles of barium chloride to the number of moles of water. It's considered as empirical formula calculation, another empirical formula calculation. Mass of barium chloride, as I told you, 32.08 minus 30, it's 2.08. Mass of water, 32.44 minus 32.08, it gives 0.36. Now, let's try empirical formula. 2.08, 0.36, divide by MR of each one, gives MR of barium chloride 208, MR of water 18, gives 0.01 to 0.02. Divide by the smallest to get the whole number ratio, gives 1 to 2. So barium chloride dot 2 water. You found now number of water. How can you be sure that all the water has been driven off? The best way to do this is to heat to constant mass, as I told you before. Heat to constant mass. You heat the crucible and weigh it again. Keep doing this until mass remains constant. If the mass has gone down after heating this, there may be water still present. When the mass remains constant after heating, you know that all the water has been driven off. You may ask it about this part. Heat to constant mass. Remember this. Calculations using mole, chemical equations, and the masses of substances. Very important part. If you have chemical equation like this one, CH4 plus 2O2 gives CO2 plus 2H2O. We can say that one molecule of methane combines with 2 molecules of oxygen to give 1 molecule of carbon dioxide and 2 molecules of water. When doing calculations using moles, we can say that 1 mole of methane reacts with 2 moles of oxygen to give 1 mole of carbon dioxide and 2 moles of water from the balanced chemical equation, from the coefficient present in balanced chemical equation. We can also tell by grams, by MR, using MR of each one. This means 16 grams of methane react exactly with 64 grams of oxygen, 2 moles, multiply 32, to give 44 grams of carbon dioxide, 1 mole, and 36 grams of water, 2 moles. When we talk about calculations involving only masses, typical calculation, you will give you mass of starting material and ask it to calculate how much product you are likely to obtain. You will also find examples done in reverse. Told you the mass of product and ask to find out how much of the starting material you would need. In almost all cases, you will be given the equation for reaction. Equation must be provided to ensure that you can solve the problem. Let's start with the first one, a problem involved heating calcium carbonate. When calcium carbonate, CaCO3, is heated, calcium oxide is formed. Imagine that you want to calculate the mass of calcium oxide produced by heating 25 grams of calcium carbonate and the AR of each one provided. Steps. Just 3 steps. Calculate the number of moles using the mass given. Mass given is calcium carbonate, so we have to calculate number of moles of calcium carbonate. Use the chemical equation to work out the ratio, the number of moles of substance you need. We need, in this case, calculate the mass of calcium oxide, we need calcium oxide. Convert the number of moles to mass. Again, first step, just calculate the number of moles using the mass given. The given mass is 25 grams of calcium carbonate, so we can calculate number of moles of calcium carbonate. Mass over mass of 1 mole. Mass of 1 mole is 100 from calcium 40 plus 12 plus 3 multiplied 16. So we have the number of moles of calcium carbonate. Ratio 1 to 1 as you can see, so same number of moles of calcium oxide. From the chemical equation, you will find that 1 mole of calcium carbonate gives 1 mole of calcium oxide. If you start with certain moles of calcium carbonate, you will obtain the same number of moles of calcium oxide. So 0.25 mole of calcium carbonate gives 0.25 moles of calcium oxide. As you can see, number of moles of calcium oxide will be the same, 0.25, but MR is equal to 56. We can convert it into mass just by multiplying number of moles by mass of 1 mole. 0.25 multiplied 56 gives 14 grams. So the reaction will produce 14 grams of calcium oxide. Let's check another problem about extracting iron. The equation below for the reaction that occurred during extraction of iron. Iron is 3 oxide plus 3 carbon gives 2Fe, 2 iron plus 3 carbon monoxide. Calculate the mass of iron which can be formed from 1000 grams of iron oxide. Given iron oxide, you have to calculate MR of iron oxide. You are given mass of iron 3 oxide. You can calculate number of moles. Number of moles equal 1000 divided by mass of 1 mole, which is 160. 2 multiplied 56 plus 3 multiplied 16. Then 6.25 moles. But take care, he asked about mass of iron. And now the ratio is not 1 to 1. We have 1 of iron 3 oxide. We have 1 of iron 3 oxide and 2 of iron. So number of moles can be written right here, 6.25, and find this by just a cross multiplication. So you have to multiply 6.25 by 2 to get the moles of iron. From the equation, we can see that 1 mole of iron 3 oxide gives 2 moles of iron. So if you have a certain number of moles of iron 3 oxide, you will obtain twice as iron. As I told you, 6.25 multiplied 2 gives 12.5 moles of Fe. Then to calculate mass, multiply number of moles by mass of 1 mole, which is 56. 12.5 multiplied 56 gives 700 grams. Take care that to find the mass of iron, we multiply the number of moles of Fe by the mass of 1 mole, 56. Common mistake you do it in exam, to multiply the number of moles by the mass of 2 Fe, 112. Common mistake. Most of students do this. But we have already used 2 in the working the ratio, so do not use it once again. Calculating the percentage yield. If you expected to get 100 grams, but you only get 80 grams, your percentage yield will be 80%. The rest has been lost in some way. We'll talk about this. This could be due to spillage, losses when transfer a liquid from one container to another, or it may be there are sorts of side reaction byproduct going on, so that some of your starting material are changed into unwanted product. This happens during the reaction in organic chemistry. Suppose that you do calculation and work out you should get 12.5 gram of copper sulfate, but you only get 11.2, not 12.5. When you actually do this experiment, 12.5 is considered as theoretical yield expected to get. Can be obtained by carrying out calculations, as we just did. 11.2 is actual yield, and this will be given to you in the question. So to calculate percentage yield, just divide actual yield over theoretical yield. Actual yield multiply 100 for sure to get percentage. 11.2 actual yield divided by 12.5 theoretical yield multiplied 100, it gives 89.6%. This means the percentage yield should always come out less than 100. In exam, it may comes out more than 100. You may made a mistake in calculation, or the question will continue. You will find that question is continue by asking you what might have gone wrong in the experiment to give a value greater than 100. If you are making a sort, possible reason is a percentage yield greater than 100 due to it was not completely dry, contain water, and water increase its mass. A student reacted, example 7, a student reacted 2.40 gram of copper 2 oxide with hot sulfuric acid. She made 5.21 gram of copper 2 sulfate hydrated form. The equation for the reaction, as you can see, first we need to calculate the theoretical yield. This is done by carrying more calculations. He mentioned student reacted 2.4 or 40 gram of copper oxide, so you can calculate the number of moles by dividing mR of copper oxide. Dividing mass over mR gives the number of moles. Number of moles of copper oxide, the same as copper 2 sulfate, the same as hydrated form. From the first equation, we can deduce that 0.03 mole of copper oxide produce the same as copper 2 sulfate. From the second equation, the same moles of copper sulfate pentahydrate. So, mass of copper sulfate pentahydrate, just multiplying mass of 1 mole times number of mole, it gives 7.53 gram. Remember that 7.53, which is calculated, is considered as theoretical yield, while this one actual yield. So you can get the percentage yield by dividing actual yield 5.21 over theoretical yield 7.53, multiply 100 to get the percentage yield. Let's start talking about chemical formula equations and the calculations part 2. In part 2, we'll talk about calculations involving gas volume and solutions. Let's talk about Avogadro's law. Avogadro says that equal volumes of gases at the same temperature and pressure contain equal number of molecules. Look at this. In this example, as you can see, we have 3 identical flasks containing different gases, chlorine, nitrogen dioxide, and hydrogen, at the same temperature and pressure, so all of them contain equal number of molecules. All of them contain equal number of particles, and this is considered as Avogadro's law. So, Avogadro said that equal volumes of gases at the same temperature and pressure contain equal number of molecules. You can see how this works in chemical reactions like methane, for example, react with oxygen to form carbon dioxide and water. This equation for the reaction CH4 gas plus 2O2 gas gives CO2 gas plus 2H2O liquid. Water is not included with us. So we need 2 oxygen molecules to react with CH4 molecule, each CH4 molecule. So if we react 100 cubic centimeter of CH4, we will need twice the volume of oxygen. So you will need 200 cubic centimeter of oxygen gas to react exactly with 100 cubic centimeter of methane and to form 100 cubic centimeter of carbon dioxide. Remember that you can use volume instead of mole in case of gases, not liquid or solid. Units of volume of gases or liquids are measured in cubic centimeter, cm cubic, or cubic decimeter, dm cubic, or even liter. 1 liter is equal to 1 cubic decimeter or 1000 cubic centimeter. But in this case, we'll talk about 1 cubic decimeter and 1 cubic centimeter as we mentioned. 1 cubic decimeter is equal to 1000 cubic centimeter. To convert from cubic decimeter to cubic centimeter, you have to multiply by 1000. And to convert from cubic centimeter to cubic decimeter, you have to divide by 1000. The most important, you need to convert them. You have to memorize this and you will need to convert them. The volume occupied by 1 mole of a gas. 1 mole of any gas contains same number of molecules, so occupies the same volume as 1 mole of any other gas. All gases, 1 mole of any gas occupy same volume at the same temperature and pressure. At room temperature, we'll talk about room temperature and pressure. The volume occupied by 1 mole of any gas is 24 cubic decimeter or 24,000 cubic centimeter. So the volume occupied by 1 mole of gas is called molar volume. And here you can also use a triangle to convert between volumes and number of moles of gases. Check this. Number of moles multiplied molar volume will give the volume of gas. If you want to calculate number of moles, you can divide volume of gas over 24 in case of cubic decimeter, or volume of gas in cubic centimeter over 24,000. You can use it if the unit of volume of gas in cubic decimeter, use it as 24. If cubic centimeter, use it as 24,000. If you want to calculate volume of gas in cubic centimeter, multiply number of moles of gas by 24,000, as you can see, and we will get some examples. Calculation with molar volume. Calculating the volume of a certain number of moles. He asks about calculate the volume in cubic decimeter of 0.2 mole of carbon dioxide at RTB. RTB, room temperature and pressure. Volume is equal to number of moles multiplied molar volume. Number of moles 0.2. He asks about volume in cubic decimeter. So volume will be 0.2 multiplied 24 is equal to 4.8 cubic decimeter. Calculating the volume of a given mass of gas. Calculate the volume in cubic centimeter of 0.01 gram of hydrogen at RTB. AR of hydrogen 1, and 1 mole of hydrogen has mass of 2 gram. So you can calculate number of moles just dividing mass 0.01 over mass of 1 mole. 0.01 over 2 equals 0.005 mole. He asks about volume in cubic centimeter, so volume is equal to number of mole multiplied molar volume, which is 24,000 this time because he wants volume in cubic centimeter. So 0.005 multiply 24,000 will give 120 cubic centimeter. Calculating the number of moles from a volume. Calculate the amount of moles in 120 cubic centimeter of carbon dioxide. Easy. Volume given in cubic centimeter, so you have to use volume, molar volume of gas as 24,000. Number of moles is equal to volume of gas divided by molar volume. volume of gas provided in this case 120 cubic centimeter, molar volume 24,000, it will give 0.005 moles. Using the molar volume in calculations with chemical equations. In order to do these calculations, we follow the same method as we used in the previous chapter, which in this video also. Calculate the number of moles of anything you can. Use the chemical equation to get the ratio, to deduce the number of moles of what you want, then convert the number of moles to the required quantity, whatever he asks about mass or volume in the question. Let's try this one. Calculate the volume. He asks about volume of carbon dioxide gas produced at room temperature and the pressure when he told you excess dilute hydrochloric acid, you can ignore dilute hydrochloric acid because it's in excess. The substance that in excess is not considered as remitting, not involved or whatever. It's not determine the rate of reaction. It's not determine the amount of product. So you can ignore dilute hydrochloric acid, just 1 gram of calcium carbonate, and you can calculate MR of calcium carbonate, then number of moles, ratio 1 to 1, same number of moles of carbon dioxide, multiply whatever molar volume 24 in this case, in cubic decimeter. He didn't mention cubic centimeter or cubic decimeter. Now you will get the volume of carbon dioxide. Let's say it step by step. We have been given mass of calcium carbonate, 1 gram. So we can calculate number of moles of calcium carbonate. Number of moles equal mass over mass of 1 mole. The mass of 1 mole of calcium carbonate, MR, is equal 40 plus 12 plus 3 multiplied 16 is equal to 100. So we have mass of 1 mole and we have mass. You can calculate number of moles, 1 over 100, it will be 0.01. Then from the equation, you find that 1 mole of calcium carbonate produces 1 mole of carbon dioxide. 0.01 mole of calcium carbonate will produce 0.01 mole of carbon dioxide. To work out the volume, 0.01 mole multiplied 24, it gives 0.24 cubic decimeter. Another one. Aluminum react with dilute hydrochloric acid according to this equation. 2 aluminum plus 6 HCl gives 2 aluminum chloride plus 3 H2. What mass of aluminum would you need to add to excess dilute hydrochloric acid? As I told you, excess, ignore it. So you will produce 100 cubic centimeter of hydrogen. We have the volume of hydrogen. We need to convert it into moles. Then we get the moles of aluminium. Then we get the mass of aluminium. So we move it in reverse direction. Calculate the number of moles of hydrogen. Volume, right here, 100 cubic centimeter, and molar volume will be 24,000 cubic centimeter. So volume of hydrogen gas given in cubic centimeter, use molar volume as 24,000. Number of moles of hydrogen is equal to volume of gas, hydrogen, divided by molar volume, 100 over 24,000. Now we have number of moles of hydrogen. But remember this, 3 moles of hydrogen or 2 moles of aluminium, different ratio. So you will just add the moles of hydrogen below hydrogen. So it must be multiplied by 2 and divided over 3. So multiplied over, hydrogens, you will write it here, multiplied by 2 divided over 3, so multiplied by 2 over 3, as you can see. So the number of moles of aluminium will be 2 over 3 times the moles of hydrogen. Now you have the moles of aluminium. By multiplying the number of moles of aluminium by the mass of 1 mole of aluminium, you will get mass of aluminium. Last part. I'm getting tired. Okay. Working with solution concentrations. When we talk about concentrations, it can be measured either in gram per cubic decimeter or mole per cubic decimeter. We can write it as gram decimeter power minus 3 or mole decimeter power minus 3, or we can say it gram per cubic decimeter, mole per cubic decimeter. You will be able to convert from gram per cubic decimeter to mole per cubic decimeter as you convert from mole to gram and the reverse, dividing by mR or multiplying mR. A sample of seawater has concentration of 35 gram per cubic decimeter. Find the concentration in mole per cubic decimeter. From gram to mole, divide by mR. So 1 mole, 58.5 mR. So 35.1 divided by 58.5, it will give 0.6 mole. What is the concentration of 0.05 mole per cubic decimeter sodium carbonate in gram per cubic decimeter? Also, you have to calculate mR, and now from mole to gram, multiply mR. Let's say 0.05 multiply 106, it will give 5.3 gram per 1 cubic decimeter, as you can see. What is the concentration in mole per cubic decimeter of solution containing 2.1 gram of sodium hydrogen carbonate in 250 cubic centimeter? He asked about concentration in mole per cubic decimeter. You have to convert this one to mole at the beginning and then divided by volume because it's 250. Remember that volume must be in cubic decimeter in this case. So mR is 84 and number of moles 2.1 divided by 84. Now you have number of moles. Don't do it like this. Just divide number of moles over 0.25. He just mentioned multiply it by 5, but it's the same. Multiplied by 5, it's like you can try it as 0.025 divided by 0.25. This value divided by 1000. You will get the same answer, which is 0.1. خليني اكتبها بخط احسن شوية. 0.025 number of moles divided by 0.250 is equal to 0.10 mole per cubic decimeter, and this is the answer. So number of moles is equal to concentration multiplied volume. Number of moles N is equal to concentration multiplied volume. And if you want to calculate concentration, this part is equal to number of moles divided by volume, but volume must be in decimeter cube. Working out number of moles from volume and concentration. When doing calculations involving solutions, you will often be asked to calculate number of moles given the volume of solution and its concentration. As I told you, number of moles is equal to volume in cubic decimeter multiply concentration. We say it CV. Because concentration is usually given in unit mole per cubic decimeter, volume may be given in cubic centimeter. You have to convert in this case from cubic centimeter to cubic decimeter by dividing over 1000. Calculate the number of moles in 50 cubic centimeter of 0.1 mole per cubic decimeter. 50 divided by 1000, then multiply volume by concentration to give number of moles. أنا بعتذر إن طولت عليكم في الفيديو ده بس عشان نخلص المولز، وهحاول الفيديو اللي جاي أغير الترتيب شوية عشان لو حد هينام بدري هغيرك الترتيب شوية، وهحاول أنزلك الأورجانيك لأن هو تعتبر أهم حاجة، وبعد كده ممكن أنزل الإنرجيتكس اللي هو شابتر 3 أو اللي هو بارت 3، وبعد كده لو في وقت إن شاء الله نحاول ننزل الجزء التاني. طيب calculations with equations involving solutions. بيجي هنا رايم سكيل، الجير كده can be removed from electric kettle by reacting it with dilute acid, let's say ethanoic acid, which is called vinegar. Calcium carbonate plus ethanoic acid gives calcium ethanoate plus carbon dioxide plus water. What mass of calcium carbonate can be removed by 50 cubic centimeter of ethanoic acid? Its concentration 2 mole per cubic decimeter. Now you can just divide this over 1000 and multiply volume by concentration to get number of moles. Ratio 2 to 1. So you calculate number of moles of ethanoic acid, multiply 1 divided 2. Now you have number of moles of calcium carbonate. Multiply its MR, you will get the mass. So calculating number of moles of what we can, then use chemical equation to work out number of moles of what we want, then convert number of moles to what is required in question. Look at this. Number of moles equal volume in cubic decimeter multiplied concentration. You have to convert volume by dividing 1000 from cubic centimeter to cubic decimeter. By concentration multiply 2 gives 0.1 mole. You will write 0.1 blue ethanoic acid, so multiplied 1 divided 2. So it will be divided 2 to give 0.05 mole of calcium carbonate. Then multiply by MR, number of moles by MR of calcium carbonate, you will get 5 gram. So ethanoic acid reacts with 5 gram of calcium carbonate. وصلنا titration. Titration like this image. This one making titration and check the endpoint of methyl orange as indicator. So calculation from titrations, acid alkali titrations. Titration is considered as technique that is used to find out how much of one solution react with certain volume of another solution of known concentration. Let's say a solution of alkali, like NaOH for example, is measured into conical flask, like the one he was holding, using a pipette for accuracy. An acid is run in from burette, swirling the flask constantly. Towards the end, the acid is run in a drop at a time until the indicator just changes color. If you know the concentration of either acid or alkali, you can use results of the titration to find the concentration of the solution reacted with. Let's try example to do this. Standard calculation, 25 cubic centimeter of 0.1 mole of sodium hydroxide required 23.5 cubic centimeter of dilute hydrochloric acid for neutralization. He asks about concentration of hydrochloric acid. We have concentration and volume of sodium hydroxide, but remember to divide over 1000. Now you have the number of moles of sodium hydroxide. Ratio here 1 to 1. Same number of moles as HCl. He asks about concentration. Concentration is equal to moles divided by volume, but remember, volume must be in cubic decimeter. So once we found the number of moles of HCl, we can work out concentration by dividing moles over volume. And remember, volume must be divided over 1000 to convert it into cubic decimeter. You will find the answer 0.106. Slightly harder calculation. Why it's harder? Because the ratio is not 1 to 1. You can do ratio, it's not hard. 25 cubic centimeter of sodium hydroxide solution of unknown concentration titrated with dilute sulfuric acid of concentration 0.05 and volume 20. Required to neutralize the alkali. Find the concentration of sodium hydroxide and the ratio not 1 to 1. He found that 20 of acid divided by 1000 multiply concentration, 20 divided 1000 multiply concentration, gives 0.001 mole. Remember, 0.001 mole under the acid, so it must be multiplied by 2 to get NaOH, moles of NaOH. Now we have moles of NaOH and we have volume 25, but must be divided by 1000. So you will get 0.002 divided by 0.025. You will get 0.08 mole per cubic decimeter for NaOH. Another example, calculate the volume of 0.1 mole per cubic decimeter of sodium hydrogen carbonate needed to neutralize 20 cubic centimeter of 0.125 mole of hydrochloric acid. Ratio 1 to 1. Number of moles of hydrochloric acid 20 over 1000 to convert it. Then multiply concentration gives the moles of hydrochloric acid. The ratio is 1 to 1, so the same number of moles of sodium hydrogen carbonate. And now he asks about volume. Volume is equal to number of moles divided concentration. We have concentration, we have number of moles, now we found the volume. Volume in cubic decimeter, you can convert it into cubic centimeter by multiplying 1000. So volume of sodium hydrogen carbonate will be 25 cubic centimeter. كده نقدر نقول ان احنا خلصنا المولز. انا بعتذر الفيديو ده للاسف هو زاد عن الساعة، بس معلش استحملني، انت امتحانك بكرة واتمنى ان شاء الله المراجعة دي تكون قادرة انها تساعدك، واتمنى تدعيلي دعوة حلوة بظهر الغيب على قد المجهود اللي انت حاسه في صوتي حتى، وشد حيلك ان شاء الله هتعمل كويس. وهعمل بريك شوية صغيرين واعمل لك فيديو للأورجانيك عشان تضمن درجة كويسة ان شاء الله في امتحان بكرة. اشوفكم على خير ان شاء الله. السلام عليكم.